many faces over here, and that's wonderful. And I want to thank Erica and her team to spare this room and this time for this purpose. I think it's very important that we provide enough opportunity for students to tell you what they have done, for us to hear their presentations and really get to know a little bit about these students. So I think it's great that we are all here. So thank you again for coming. And I want to thank Josie for doing a lot of the background work. I think she's done a wonderful job, and she and her team, they're all doing a great job. Thank you very much. We'll get started, Josie. All right.
We'll have our first presenter come up.
Yep. The first student is from the University of NC State, my favorite school.
We can't say that.
No? Okay. All right. All right, forget it. Scratch that.
There's no bias in these competitions.
No, I said my favorite school. I didn't say my school.
Oh.
Okay, then I'll have to take you all the way back to India.
Oh, true. Good point. Welcome.
Noor, please come on. So we have Noor Shafa Mazumdar.
Yes.
From Wilson College of Textiles. And his paper is about the firefighters' protection. I'm not going to go through more details on that one, other than just saying it is how to protect our firefighters. With that, please welcome Noor as he gives his presentation.
Yeah.
Great. Thank you.
Good afternoon, everyone. So my name is Noor Majumdar. I'm a PhD candidate and working with Dr. Brian Herman in Wilson College of Textiles at NC State University. So as you can see today, I'll be talking about the PFAS, their assessment in firefighter turnout gear textiles. So at the beginning of the presentations, I would like to talk. Sorry, I think the clicker. Yeah. Okay. All right. So sorry for that. So what is PFAS? So PFAS is par and polyfluoroalkyl substances, meaning fully or partially alkyl substances. So you can see there are two examples of fully fluorinated alkyl substances, PFOA and PFOS. So why I'm talking about PFAS today? So International Association of Research on Cancer, they have classified the firefighters' occupations as a group 1 carcinogenic, meaning that the occupational exposures to firefighters is now known to cause cancers to human. The same association in the year later, in 2023, classified PFOA as a group 1 carcinogenic and PFOS as a group 2B, meaning possibly carcinogenic. That means now we know that 2 PFAS are at least carcinogenic and firefighters are getting exposed to PFAS. So now the question arises, are the firefighters getting cancers because of their higher exposure to PFAS? The answer could be partially yes. Several studies have shown that firefighters have elevated PFAS levels in their blood serum. So now let's talk about the exposure sources. What are the sources that firefighters actually get exposed to these carcinogenic chemicals? So one of the main potential sources is air and dust of the fire scene and fire stations. Whenever they go to a fire, they expose. They also bring back some contamination to the fire stations, so they can be exposed. Other thing is like AFFF or aqueous field forming foam. They can be also exposed to PFAS from this foam itself. More interestingly, the turnout gear itself, the gear they wear to protect themselves, is also treated with PFAS to provide you repellency and performance. So they can be exposed to PFAS from their gear itself. So in today's talk, I'll be mostly talking about how the firefighters can get exposed to PFAS from their turnout gear. So now, since we have talked about a little bit of the background, let's talk a little bit about the firefighter turnout gear. So the structural turnout gear that firefighters wear has actually 3 different layers: the outer shell, moisture barrier, and the thermal liner. So each layer has their own purposes. If you see the outer shell and moisture barrier, both of these layers has the repellency performance requirement. That means to provide the repellency, PFAS is actually used in these 2 layers. The third layer, thermal liners, is mostly for the comfortability and moisture or sweat management. So to provide the repellency in the outer shells and the moisture barrier, you can have PFAS treatment. So basically for the outer shells, you can have side chain fluorinated PFAS. So we are saying these side chain fluorinated PFAS because your main backbone chain is not fluorinated. Only the side chain, those are attached to your main chain, can be fluorinated. For the moisture barrier, the most famous barrier is the PTFE or Teflon. So it's a polymeric PFAS because your main polymer chain is fluorinated. However, the barrier cannot be used by itself. You need a support. So usually a textile is used to support the barrier. That textile site can also be treated with the PFAS chemistries, depending on what are the requirements you want from the moisture barrier and also the manufacturer, which products you are getting. The thermal liners usually is not treated, but it also can be treated. It's very, very manufacturer dependent. So now, since we have talked about the backgrounds and introductions, let's talk about the goals of this study. So I had two goals for this study. Let's talk about the first goal first. I wanted to evaluate PFAS and total fluorine in outer shell fabric in new and washed conditions. And to do that, I actually selected fabrics manufactured between 2003 to 2024. So I actually selected a wide range of years so that we can understand how the chemistry actually evolved or changed over the years. And also I wanted to do the washing as well, just to see what are if the PFAS have any impact after the washings. So for doing that, I actually selected 13 different outer shell fabrics from 4 different manufacturers. So these are all US-based manufacturer, except this manufacturer C, that 2010 one, we got these fabrics from a European market. Other than that, all the textiles was from US-based. So once now I have the fabrics in new conditions, I also wash them 25 times so that I have both new and washed fabrics. After washings, I started my analysis. So my first analysis was non-volatile PFAS. So for doing the non-volatile PFAS, this is the flow chart, how I prepare the samples. I will not go through in detail of each of the process. However, I just wanted to give some ideas that from your fabric until your samples are ready to run in the mass spec, it takes a couple of weeks, depending on how many samples you are working with. Once you have your samples, you run it in a mass spec. That may take another couple of weeks, depending on how many samples you have. So for the non-volatile PFAS analysis, I actually used liquid chromatography mass spec known as triple quad LCMS or LCMS-MS. I use this instrument because in our lab, we do have a method developed using these instruments where we can quantify for 50 different types of non-volatile PFAS. So once I'm done with the analysis, this is the results. So I know this is a very busy slides, but I'm going to break it down so that it's easier for us to understand. So this is a heat map. So the darker color you see, the higher concentration of PFAS was detected. And PFAS concentration given here is in parts per billion scale. The highest PFAS we detected around 3,600. On your y-axis, we have the list of the PFAS which were detected. As I mentioned, I had 50, but I did not include all of the 50 PFAS here because for textiles, not all the 50s were actually detected. So I only included the PFAS that had enough detections or consistent detections throughout the samples. On your x-axis, I have the fabrics or the samples starting from 2003 here at 2024. So if we see these red boxes are actually the fabrics in new conditions from 2003 to 2017. If we just shift one column right, that's your fabric after the washing. So it's the same fabric, but what I mean after the washing. So what's the overall trend? If we see on each fabrics in new condition and age conditions, after the aging, our detection was lower. You see, this is the new and this is the age, detection was lower. New and age, detection was lower. That means one common trend we have seen after 25 washes, whatever the PFAS, it was in new conditions. After the washes, the detection went low. And for these 3 fabrics manufactured in the recent years, I only had the new fabrics. I did not wash those because in new conditions, the detection was so low that I actually did not want to see what happens after the washings because it was very, very low, even in the new conditions. So another general trend is if you move the first part of the slide, that's 2003 until 2010, this is the darker side. That means our detection was higher until the fabric manufacturer until 2010. If we move beyond 2010, this is the lighter side of the slides. That means our detection was low. So whatever the fabrics manufactured after 2010, the PFAS chemistries or the finishing process actually optimized. So where detection was very, very low. And the recent years is the lowest, 2020, 2022, 2024. So only one difference is what we have seen with the dye PEP. It did not follow the general rule. General trend was after the washing, we detected low. For this one, you see after the washing, your detection was higher for all the fabrics. So what I anticipate is this actually comes from 2010 because it was very, very high in new conditions in 2010 fabric. And 2010 one, the European one, different than the other fabrics. And when we wash the fabrics, this fabric actually contaminated the other fabrics. That's why we detected this dye PEP to all other fabrics only after washing. So your PFAS can be transferred between our fabric to fabric. So now let's move forward with our total fluorine analysis. So I use the combustion ion chromatography for the total fluorine analysis. So sample preparation wise, this is easier compared to the PFAS analysis because PFAS takes a lot of time just to prepare the samples. This is just combustion. So with the weigh the fabrics and put it in the chamber, it combusts everything at 1000 degrees Celsius, break down every bond. Then I just look for fluorine. We can look for other anion as well, but for this study, I was very interested just to see how much fluorine we have. So here is our results. So if we see if the fluorine results agrees with the PFAS, somewhat yes. You see higher fluorine concentration was the fabric manufactured before 2010. So that agrees with our PFAS results. And then if we move beyond 2010, our total fluorine was lower. That also agrees with our PFAS. Only thing is different is 2010 one. It's the lowest one. Again, it's a very different fabric, so we cannot say, we cannot directly compare it with the other fabrics. And one another general trend is your new and age or new and wash fabrics. After washing, our total fluorine was lowest or lower compared to the new conditions. So that also matches with our data with our PFAS analysis. So now let's talk about my second goal. Second goal, same. I still wanted to do the PFAS and total fluorine analysis, but now I'm interested to see it all three layers in the outer shells, the moisture barrier, and the thermal liner. So to do that, I actually selected three materials for three layers, one for outer shell, one for moisture barrier, and one for thermal liner. Both the outer shell and moisture barrier was known to have PFAS treatments, and the thermal liners we got did not have any finishes. So it did not have any intentionally added PFAS. So I wanted to see the PFAS in new and age conditions. So to simulate the aging, we actually exposed the fabrics in UV weatherometer, then did the thermal exposures at 180 degrees Celsius and washes it 12 times. We actually did the UV exposures here at UL. So I repeated the whole process one more time. So we ended up with 60 hours of UV, 2 hours of heat, and 24 washes. So after that, we now have the age fabrics. We had the new fabrics. So once we have both the fabrics, I started with the non-volatile PFAS analysis. So same technique as I mentioned in my goal one. So here is the results. So the same heat map on your y-axis, you have the PFAS, x-axis, you have the fabric. So these are your fabrics, outer shell in new condition, moisture barrier in new condition, thermal liner in new conditions. Just move one column right. That's the same fabric after the age conditions. So the common trend here is the same as the washing. What we saw in the washing technique, after the washing, it was lower. The same here after the aging, whatever we detected in the new condition after the aging, it was lower. The thermal liner after the aging is mostly gone. I want to focus a couple of things here. First thing is the thermal liner. As I mentioned, the thermal liner did not have any PFAS treatments. However, I detected a lot of PFAS. Even it was higher than the outer shells. So these could be contaminations because thermal liner production process is comparatively complicated than the outer shell fabrics. And also I can say it's a contamination because after the aging is gone. So whatever was there, it was residuals. It just washed off during the washing. I do have further evidence. I'll talk it in the next slides. So two other PFAS, PFBS and PFBSA. These are the dye PAP in my previous goal. These also did not follow the trend. After the aging, we see that PFBS and PFBSA were higher in outer shells and the thermal liner, meaning your PFBS from your moisture barrier can transfer to those two layers. So now let's move forward with our total fluorine analysis. So same method. So total fluorine, the highest total fluorine we got in moisture barrier. Makes sense because your barrier is actually PTFE, fluorinated. And then your textile side is also treated. So we detected a very, very high amount of total fluorine. But it also follows the same rule that after the aging, detection was low. We detected fluorine in outer shell as well. It was not as high as the moisture barrier because the fabric itself is not fluorinated. Only the fluorine finishes are there. Interestingly, we did not detect anything in the thermal liner. So whatever the PFAS was there was the below limit of detections of the CIC or combustion ion chromatography. So that's your further proof that the PFAS we detected in thermal liners is actually the residuals or the contaminated PFAS. If it was intentionally added, we should be seeing something in the total fluorine analysis. So let's talk about a little bit what is the difference between PFAS and total fluorine. So this is the chemistry, durable water repellent chemistries. If we analyze these for the PFAS, you will not see anything. You will only see PFAS when there is a degradation product, when your PFAS are in a non-polymeric form. However, if this fabric you analyze in combustion ion chromatography, you combust it at 1000 degrees Celsius, you breaks down all the bonds, so you will detect everything. You will not miss anything. So that's why in the moisture barrier, it was so high because it detected each and every fluorine that's there. So with that, to wrap up, the conclusion is PFAS have been detected in all three layers. However, the outer shell and moisture barriers was intentionally added, but the thermal liner was not. Highest fluorine was detected in moisture barrier, followed by the outer shells. Low PFAS detection after aging and washing, it proves that your PFAS are being removed during those processes. And also PFAS can be transferred between the layers, what we have seen. So this is an ongoing project. I have not analyzed anything on the volatile PFAS. I mean, we are on the method development and analyzing within the next 6 months. I'm hopeful to have those results. And then we are also analyzing the fireground contaminants. So usually combust the household materials and just to see if any PFAS can come off through the smoke. With that, I'd like to thank Dr. Herman and everyone from our research group, and of course, FEMA for providing us the funding, the TPEC and Metric for giving me the opportunity to work in this very important sector, and also for Metric for working with us with the PFAS and PFAS analysis. So thank you, everyone. Thank you.
Okay, well, welcome. Our second presenter is Hassan Ali. He's coming from Karachi, Pakistan, which is our one of the newest student chapters that formed about 2 years, 3 years ago now, and it's a very active chapter. I know I have to say that only because I have to recognize this chapter's participation to the membership and to the student activities. So welcome, please carry on.
Thank you so much. All right. So if I ask you a question that what do the space missions on the high performance vehicles and the rockets have in common? So the answer lies in the power of the carbon fiber and how their thermal behavior can unlock the new opportunities or the possibilities. So good afternoon to all the delegates, attendees, and the respected judges. So I'm Hassan Ali, representing here the NED University of Engineering Technology from Pakistan, and it also representing the AATCC Pakistan section and the NED chapter as well. So my today's topic of discussion will be the prediction of effective thermal conductivity of the multi-layered plain woven carbon compost. So here's the outline, starting from the introduction, the aims and the objectives of the research. Then we will be discussing about the methodology and then the experimentation and the validation of it. And then we'll be concluding with the results and the discussion and finally the conclusion. All right. So as we discussed that the carbon fibers are used in the high-end applications and as it offers the higher strength and enhanced impact resistance properties, higher heat dissipation properties, and have the higher specific stiffness, or it can withstand the temperature of over 2300 Kelvins, and is lightweight in nature as well. The aims and objectives includes the extraction of the structural parameters by using the actual fabric and by using the image analysis technique as well. Then we'll move towards the development of the computational models of the multi-layered carbon composites. Then the heat transfer analysis to predict the behavior, thermal behavior. And then finally, we'll be moving towards the evaluation of the effect of multi-layers of the composites. And then we will do the validation of those computational models as well. All right. So that's the pictorial representation of the complete methodology opted for the project. So here you can see, firstly, the image of the actual fabric is analyzed by using those parameters, the model is developed from it, right? And by using those parameters, we have developed the unit cell of it, and that's the spline curve of the yarn. And then finally, we'll move towards the heat flux, evaluation of the heat flux and the temperature as well. All right, so the whole process, the whole methodology starts with the determination of the structural parameters by using the image analysis technique. So these are the parameters which you can see here of the actual fabrics, which includes the ends per centimeter, picks per centimeter, distance between the warp and the weft thread, thickness, and you can say the warp and the weft spacing. So these were the exact parameters which we have taken from that actual image, and then used those parameters later on in the computational models. All right. So the second stage is basically the development of the unit cell of the single and the double and the triple layer composites out of it. The influencing factors of the thermal properties of the composites includes, you can say, the fiber orientation, the yarn spacing, and the fiber volume fraction as well, and the weave style or the thermal properties of the constituent material. So these are the structures which you can see here we have developed. That is the single layer structure, that's the double layer structure, and that's the triple layer structure. So then for the heat transfer analysis, the unit cell is developed by using the spline curve, which you can see here. Sorry. You can see here, right? So that's the spline curve by using the lenticular cross section of the yarn, as you can see here in the first image. And then in the second image, the material orientation is assigned into that yarn of the carbon fiber, and which is used to simulate the non-linearity or the waviness in the yarn on the cross section as well. So these are the equations which you can see here. We have used to determine the thermal conductivity of the composites in the transverse and the axial direction as well. So here you can see the heat flux distribution of the single layer structure, that one, and the double layer structure and the triple layer structure as well. Right, and the fiber volume fraction was set to the 60% originally. So it is evident from the results which we have got that the heat flux reduces as we increase the layers of the composites. All right, so here's the pictorial representation of the temperature distribution for the first, second, and the third layer structures with a fiber volume fraction again of the 60%. And as the heat flux and the temperature are directly correlated with each other, right? So the temperature generation also reduces as we increases the layers of the composites. So now for the experimentation part, the values of the fiber volume fractions were varied from the 70% to the 60 to 90%, which was originally the 70%, right? So in order to determine the effect of these varying values over the effective thermal conductivity. And after which the effective thermal conductivity is evaluated and validated. So what we have found that the effective thermal conductivity has increases with increase in the fiber volume fraction, as you can see here in the pictorial format, right? So due to the increment of the fiber content. So as we know that the effective thermal conductivity of the air is greater as compared to the fiber. So the fiber content, as you can increase the fiber content in a certain cross section of a yarn, so the thermal conductivity will also increases as well. And that's for the thermal resistance. So obviously it would get decreased with increase in the fiber volume fraction. As we can increase the fiber volume fraction, so the thermal conductivity and resistance have the inverse relation. The reason behind, again, the air is more thermal resistance as compared to the fiber. So due to which, as we increase the fiber volume fractions, the thermal resistance will get increased as well here. All right. So now for the second part, up till now we have discussed about the effect of the fiber volume fraction over the thermal conductivity, that how it behaves and how the carbon fibers actually conducts in the one layer, second layer, or you can say in the third layer structures as well. So now that's for the second part. As we increases the layer, what has its effect over the thermal conductivity? So as we know that the thermal conductivity is an intrinsic property and the resistance is an extrinsic property. So thermal conductivity remains constant as we increases the number of layers, right? For the similar amount of fiber content in the certain cross section of a yarn. So that's the result part. So you can see that the thermal conductivity is almost the same for all the layers here. And while the thermal resistance gets increases as we increase the layers, which obviously explaining the effect which I am talking about. The thermal conductivity is an intrinsic property and the resistance is an extrinsic property. So the overall error percentage was less than the 5% as we compared to the actual fabric of it. So here are the conclusion remarks of the study. That the effective thermal conductivity of the multi-layered carbon composites were predicted by developing the unit cell of it and varying their values from the 60% to the 90%. And typically, we can say a higher fiber volume fraction in the cross section of a certain yarn results in an increase in the value of the effective thermal conductivity and decreases in the value of the thermal resistance in all the layers individually, right? So then we can say that the increase in the number of layers and in a constant effective thermal conductivity has an effect, while the thermal resistance gets increased due to it. And the predicted results will finally then compared to the actual fabric. The results, the mean absolute error we get was less than the 5%. And the structure, which was obviously due to the human error, or you can say the environmental error. That's it from my side. Thank you so much.
Here's our third presenter. Get that presentation set up.
Okay, and our third presenter comes to us from University of Georgia, Yahya Absalon.
Yes,
Is that how?
Yes.
Did I pronounce it right?
correct.
Great. And his presentation, I'm sure you already see on the board to see what he's going to talk about. And please join me to welcome him. Thank you.
Thank you. Hello, everyone. Thank you for having me. Well, for my presentation, I'm going to actually to present novel and promising method, which I believe that in future we will hear about it more, which is a photocatalytic actually method for removing textile dyes by a novel oxide nanoparticle, which comes from actually the parent crystal is titanium oxide, which is doped with different elements. So I believe that because I'm going to speak about textile dyes, so it is good if we know something about textile dyes. Actually, textile dyes are substance used to color textiles such as fiber, yarn, or fabric. There are a lot of benefit for textile dyes, which make them very, very important. And I just brought some of them. The first one actually is aesthetic. Dyes enhance the visual appeal of textile by providing vibrant, consistent, and actually diverse colors. On the other hand, identification is another significance of textile dyes. A different color can signify different things in actually various culture or profession. Also, actually, protection application of the textile dyes is another application of that, which such as, for example, ultraviolet protection or antimicrobial properties. Enhancement of material value. Of course, fabric with which is dyed can be actually have actually more value than the undyed fabric. Durability is another properties of the textile dyes, and actually modern dyes, when applied correctly, can retain their color and intensity through many washes and also prolonged exposure to environmental factor. And the last one, which I believe this is very, very important, is psychological and cultural significance. Color often actually carries deep psychological and cultural or religious significance. According to the actual researchers, there are 5 countries which they produce the highest amount of textile dyes, such as China, India, US, Brazil, UK, and Germany. And according to the global textile dyes market, it was around $9 billion was actually consumed for producing textile dyes in 2023, and it's assumed that it will be increased to even $15 billion for actually textile dyes. So as you can see, actually around 90% of the textile dyes are obtained by industry, and just 10% of them are obtained through actually natural sources. So there are some news. The first one is that based on a research in 2022, actually around 1.3 trillion gallon of water was consumed just in textile dyes industry. And according to the World Bank estimation, it is around 20% of all the water in the world, actually. So there are a lot of disadvantages comes with textile dyes, actually, although there are a lot of properties and application for them, such as environmental pollution. Textile dyes actually effluent often contain toxic chemicals. On the other hand, toxic chemicals, some textile dyes contains carcinogenic compound, poisonic potential health risk, and resource depletion. There are a lot of water has to be consumed during the process of textile dyes. Energy consumption, of course, a lot of energy need to be consumed to produce textile dyes. And non-biodegradable residue, actually, this persistence of dye can lead to accumulate of harmful substance in actually ecosystem. Air pollution, producing actually releasing VOC, volatile organic compound, is another disadvantages of the textile dyes. Also, it can affect badly on workers who work in textile dyes, especially it can affect on the actually respiratory issue. They have some respiratory issues or a skin problem. And waste generation. And the dyeing process actually generates solid waste in the form of dye residual, sludge, and unused dye. So as you can see, actually all of those disadvantages make our world actually not a very pleasant for living. So there are we cannot actually avoid producing textile dust because actually it is a very, very important industry, and it has a lot of application in different industry. Also, we cannot use just natural sources because of the limitation, and also because of the because of the limitation, we cannot use natural sources. So there are a lot of methods are actually invented for removing textile dust from water when it enters to water. And all of those actually are categorized into three different categories of physical method, chemical method, and biological method. Actually, all of the researchers shows that almost all these method belonging to these categories. But the problem with this actually method are, first of all, they cannot remove entirely textile dust from water. The second thing is that some of these methods actually are very slow. So we need to consume a lot of energy to actually remove textile dust. And also some methods such as chemical method, they produce some side product, some sludge, which actually make another problem for us. So by this method, actually, I'm going to introduce more a method which is a combined method, and this is a photocatalytic method. But what is photocatalytic method and how actually they work? Is it a kind of my introduction? Actually, first of all, what is photocatalyst? Photocatalyst is a kind of catalyst can accelerate reaction. We know that catalyst, the first purpose of catalyst is accelerating a reaction. Photocatalysts are a kind of catalyst can actually work under a type of light. So actually, and when exposed to light, photocatalysts initiate and drive chemical reactions without being consumed. So they don't have to involve to the reaction, and also they don't have to be consumed during the reaction. And then most actually common photocatalysts are semiconductor. Why semiconductor? Because of all the parameters which we need for a photocatalyst, such as proper energy band gap, surface area, and a recombination of electron from conduction band to valence band. All of them can be found in actually semiconductor. So regardless of the type of the photocatalyst or how what is the application, all of the photocatalytic reaction, they have some key which are common for all of them. Okay, the first step is actually light absorption. So you just imagine that this is a photocatalyst which is in water, which is polluted with textile dyes. So this is our photocatalyst with the energy band gap, which is between, it can be in UV or visible light, actually wavelength. So the first part is light absorption. So as you can see, light can be actually photocatalyst can be exposed by the light, which is I believe that the most and powerful and cheapest and available type of energy is sunlight, which we can use it. And then in the next part, electron excitation is happening, which actually electron from valence band are excited during the energy which they actually accept from the sunlight. They excited to conduction band, and then because of because actually the electrons excited to conduction band, so we have some positive charge in valence band. So in the next part, actually redox reaction is happening. Which, if you want to find out how actually these species are produced, you can follow the left side of the, actually the chemistry are coming into the left side. So the first species is superoxide, of radical, which is because of the reaction of oxygen with the electron. And then the next one is single oxide, which is because of the oxidation of the superoxide. The next thing which can be actually happening is a reducing of the superoxide radical, which can actually produce hydrogen peroxide. On the other hand, actually water also can react with the positive charge to actually obtain some hydroxyl radical. and also hydroxyl superoxide hydrogen peroxide during the reduction can produce hydroxyl radicals. So as you can see, there are different radicals, different species can be obtained, which they actually use. One of them actually in each of the photocatalyst reaction, one of them can be obtained, and it can goes to react with the textile dyes to abstract a hydrogen from it and to decompose the textile dyes. So converted actually to water and dioxide carbon. So this is actually the reaction which is happening here. So what we did, it was a synthesizing of a novel oxide nanoparticle, which comes from the actually doping with it was actually the parent crystal was titanium oxide, and which was doped with the cobalt, cerium, and nitrogen. And the method was it was actually a very common method, which is industrial, and also industrial method, which is a solvothermal or hydrothermal method. And it was actually, we need to find out how we can actually produce, what is the best concentration for the precursor, and then we need to transfer it to autoclave, and then at a special time and temperature, and then centrifuge, drying, and then finally calcinating. So as you can see here, this is actually the physical characterization of that. So the oxide nanoparticle was in the corresponding phase, which was anatase phase, which was a kind of oxide dioxide titanium. The size of the crystal was 10.2 nanometer, which was very, very small. And because of that, actually, it can produce a very high surface area. Also, the FESCM shows that the shape of a nanoparticle was like sheet, which provide more surface area for the energy for the photocatalytic reaction. On the other hand, optical characterization was also carried out by, first of all, DRS shows that actually how the DRS is the diffuse reflectance spectroscopy, which shows that actually how it is very, very lower than dioxide titanium as a very well-known nanoparticle. So it actually conferred the high absorption in visible wavelengths, which is the most part of the sunlight. On the other hand, it shows that the energy band gap is around 2.5, while for dioxide titanium is around 3.5. Also, recombination of electron, which is a very usual and common problem for photocatalysts. It shows that how it is very, very lower than dioxide titanium, the peak. So recombination of electron from conduction band to valence band happening very slow, which is very good actually. And also surface area shows that it is around 85.3, actually has the surface area of 85.3. So what we did, first of all, we actually provide our photocatalytic reaction. So as you can see, it has two lamps. One of them is on the roof, which is 100 watt, and the other one are some tube lamp, which have actually 10 watt. And then we actually try to find out what is the best condition for removing textile loss from water with our photocatalyst, which actually we tested around 81 condition, and with different parameters which are very important in photocatalytic reaction. And then finally, actually, we found out actually how our photocatalyst could reduce the textile loss from water after 2 hours to zero, actually around zero. It was around 98%, which after just 2 hours, it could reduce all the textile loss from water to around 98, or actually we can say 100%. So as a conclusion, in this study, actually, we investigated the synthesis of a novel photocatalyst, and due to the high crystallinity of nanoparticle and low actual energy band gap, this photocatalyst can absorb visible wavelength. So we can actually use sunlight. It can be exposed by sunlight, and different effective parameters such as pH, temperature, dosage of textile catalyst, and concentration of textile loss were actually all of them were optimized to find out the best condition. And according to the result in the basis environment, at room temperature, the photocatalyst can remove textile loss at short time. So yeah, it was all of my presentation. Thank you so much.
Thank you so much, Yaya. And we'll have our fourth and final presenter please come up. See if I can-
All right, please join me to welcome our last presenter, Melissa Armstead from NC State University. And I think she's got an interesting paper just like the others. So please carry on.
Thank you very much. So I'm Melissa Armstead. I'm a PhD student working with Dr. Brian Orman over at NC State, very close by, and I'll be talking about respiratory protection for wildland firefighters. So recently, we've been seeing more extreme wildfire behavior, and this is largely due to the impacts of climate change, the heavy fuel accumulation we've seen, and also the expanding wildland-urban interface. And that's the area where vegetation interacts with structures. And so essentially, this development of the wildland-urban interface places us at a greater risk during this increased wildfire behavior. So we're seeing not necessarily more fires, but more extreme fires that are burning larger acreage. And so we're relying more and more heavily on our wildland firefighters to help contain these fires. And so our firefighters face a number of different exposures in the field. I'm primarily going to be focusing on smoke exposures, so the combustion byproducts from burning vegetation. And those typically can release a number of toxicants like carbon monoxide, particulate matter, PAHs, and VOCs. Then when we start to get into that wild and urban interface, we introduce new compounds like metals and plastics and other building materials that interact in that dynamic smoke mixture, which can be really toxic when inhaled. Today, I'm primarily going to be focusing on particulate matter, and more specifically PM 2.5. So we hear this a lot in air quality standards, and what it is are these very small particles, 2.5 micron or less in diameter, that are able to penetrate deep into the respiratory system when inhaled, where they can then be transported rapidly throughout the body. Now, there have been studies that have linked the exposures to PM 2.5 to respiratory and cardiovascular diseases, not just in wildland firefighters, but also in the general public. But focusing specifically on our firefighters, as Nur mentioned, in 2022, IARC classified the occupation of firefighting as a Group 1 carcinogen due to their different occupational exposures. So we're going to be focusing on the smoke aspect, the inhalation exposures that they face in the field. Now we have to approach structural firefighting or wildland firefighting a little bit different from our structural firefighting. So in order to address those unique demands of the job, the personal protective equipment has to adapt to account for their increased workloads, that extreme environment they're in, and the long duration they're out there. So they can be out for up to 12 hours a day working on maintaining these fires, and they can be out for several weeks at a time. So their personal protective equipment is going to be a little lighter. We're not going to have the 3 layers. Instead, we're looking at a single fire-resistant layer for their shirt and pants. They sometimes have a helmet and eye protection and boots, and then everything they have to carry with them in their pack all day. But what we typically don't see here is any form of respiratory protection, despite being in that smoke all day. So when we think of respiratory protection and firefighting, we're typically thinking of our structural firefighters who wear these self-contained breathing apparatuses, or SCBAs. And what these are they supply clean air to the firefighter for a specific period of time. However, these tanks can be very heavy and they normally only last 30 to 60 minutes. So this isn't necessarily practical for our wildland firefighting applications. So looking at some of our other options for certified respiratory devices, we have air purifying respirators here, which are able to capture those contaminants as we breathe in and as they pass through the filter or cartridge. Similarly, we have our powered air purifying respirators, which work the same. The big difference here is that they're operating under positive pressure. So there's a blower that's actually blowing air into the face piece, which helps reduce some of the physiological burden. And then lastly, we have our filtering face piece respirators, our FFRs, and this is going to include our N95s. These are disposable, lightweight respirators, but they're typically focused on particulate protection, whereas our others can offer various particulate vapor protection depending on the filter or the cartridge that you use with them. So even knowing all this, unfortunately, in the United States, there is no requirement for respiratory protection for wildland firefighters right now. There is a standard, NFPA 1984, for respirators for wildland and WUI operations. However, currently nothing has been submitted for certification to this standard. So we really want to look at some of these barriers to adoption here. Now, within the standard, it does talk about different levels of protection, and this is really important to move forward. We don't necessarily need the highest protection at base camp when you're more focused on particulates here, but then operational activities when they're actively fighting wildland fires, they would need a little bit more gas and particulate protection. And then once we get into that wildland urban interface and we introduce all of those toxicants, we need additional gas protection there. So trying to bridge that gap between this barrier of adoption and our wildland firefighters, we wanted to evaluate a really wide range of products that are all commercially available right now. They're currently on the market, and a lot of them are being geared directly towards wildland firefighters. So we have all of our certified respiratory protection, which is going to be up here, our PAPRs, our APRs, and our FFRs. And then we tried a bunch of alternative products. So we have our bandanas, our gaiters, our hoods, and our face coverings. And these are all products that we tend to see more often in the field, if anything. Some people will call the bandana the current state-of-the-art respiratory protection for wildland firefighters. So these are much more common than our certified PAPRs and APRs. And what we did is we evaluated all of these devices on our animatronic head form to look at the total filtration efficiency and the breathing resistance. So we moved the head form into a controlled environmental chamber and tested it under standard textile testing conditions. We generated an aerosol, and then the head form ran through a 10-minute movement protocol while breathing. We did this at 2 different breathing rates, 15 and 28 liters per minute, which are the breathing rates for light and moderate workloads. But I do want you to keep in mind that typically our firefighters are operating at arduous workloads for extended periods of time, so we would expect these trends that we see to increase. This is just a fun slide I always like to include to show you how we are able to create a simulated fit test on a head form. So essentially, we can stress the seal moving up and down, side to side, and then opening and closing the jaw to really see how these perform over our 10-minute test. Now, looking across the data, this is plotting the total filtration efficiency at both the light and moderate workloads for all of our products. And before we move too far, I do want to point out we're looking at the total filtration efficiency at 0.3 micron, not 2.5. And that's because 0.3 is largely considered the most penetrating particle size used in respirator testing. Now, it does vary a little bit from material to material, but in general, 0.3 is the most difficult particle size to capture using traditional filter mechanisms. So looking across the data set, oh, it's covered at the bottom, but that's okay. My respirators are doing very, very well. All of them are filtering 90% or above, as they are certified to do. We do have a couple exceptions there. Our 2 cup-shaped N95s weren't able to maintain a great seal to the face, and that's just one of the limitations with having our single-size head form. Some different products fit differently, but otherwise, everything's doing what we would expect, very high performance. Then we have this middle group here. And this is going to have some of our face coverings that we're actually able to create and maintain a reasonable seal to the face, which is what's giving us higher filtration there. Though there was more variability between test and also across flow rates. And then lastly, we have this group down here. These are all under 20% filtration efficiency, and this includes all of our hoods and bandanas. So what's currently being worn in the field. Now we're also able to look at the breathing cycle over time by plotting that differential pressure. So if we look here, I have the light and moderate workloads. The first thing I want to point out are the difference on the y-axis. So at 15 liters per minute, we go up to about 300 Pascal. When we get up to the moderate workload, 28 liters per minute, we go up to 800 Pascal. And this is because breathing resistance more than doubled for all of the products that we tested. So again, this is important to consider when we get up to those arduous workloads, we would expect it to continue to increase. Now, when we look at these, graphs, that top peak right here, this is going to be your inhalation resistance. The bottom peak right here is going to be your exhalation resistance. And for the most part, our products are doing what we would expect. The APR, which filters very well, has a very high breathing resistance. It's at 300 Pascal under a light workload, and then it doubles to a little under or to a little over 600 Pascal at the moderate workload. Our N95, our face covering, and our PAPR are all pretty moderate. They're under 100 Pascal at the light workload. And then once you start moving up at that moderate workload, they're under 200 Pascal. And then down at the bottom here, we have our hoods and bandanas, and this is why they're worn so often. They are a lot easier to breathe through than any of our other products. However, we did see that that does not correlate to filtration efficiency. But we can plot the two together to look at the trade-offs between protection, our filtration efficiency on the y-axis, and breathing resistance on the x-axis. So right now we're plotting the maximum inhalation resistance, which was that top peak we saw on the graph before. So ideally, we want to be somewhere in this top quadrant. We want to filter at least 50% of the particles at 0.3 micron, while also maintaining a breathing resistance that does not exceed 250 Pascal, which is about 25 millimeters of water. And there are several products that fall into this category right now. We have both of our PAPRs here, we have all of our N95s, and then we have one of our face coverings that was able to maintain a really good seal. At the lower workload, we had another face covering that fell into this category, along with our quarter face APR. And then at the higher workload, we actually had one of our gators that was able to improve filtration efficiency because the higher work rate pulled it into the mouth cavity. It was creating more of a suction effect. So it was filtering directly through the material as opposed to going around. So overall, some conclusions are that our respirators performed as we expect them to do. They filtered very, very well on the head form, but they have consequently high breathing resistances that aren't always reasonable for our wildland firefighters to wear for 8+ hours a day. The PAPRs were able to help reduce this physiological burden. However, there are still some barriers to adoption there. We have the higher cost of PAPRs, carrying them around with them all day, but they do help reduce that burden on the wearer. Then we have alternative products that may be more realistic for a base camp scenario when you're more concerned about particulate protection. They had much lower breathing resistances, but similarly lower filtration. So when we're looking at alternatives, we really want something that has a high filtering material and fits close to the face, like our one face covering there that really forces particles through the material rather than leaking around. And then lastly, a really big takeaway from this is that all of the breathing resistances more than doubled at the higher workload. So we're expecting these products to be even harder to breathe through for 8+ hours a day at an arduous workload. So it's something to consider. We need to balance protection and comfort in order to get wildland firefighters to wear something to help reduce this exposure. So with that, particulates are only one piece of the puzzle. We are still trying to do vapor testing on the head form, running the same protocol with methyl salicylate, then looking and seeing how our results correlate to actual smoke exposures in the field. And then lastly, but arguably more importantly, getting feedback directly from our wildland firefighters. So we'll be having a wear trial where they'll run through an hour-long protocol in each of our products, answer questions before and after, and we'll be doing physiological monitoring. So with that, I'd like to thank my advisor, Dr. Ormans, the research team, the project team, and of course our funding agencies.
Conclude our coursework presentation. Please stay here. We'll have a question and answer session. And Josie, you will moderate that?
Our membership director, Maria Theory, is ready to come up and moderate. Yes, to all the attendees, one of the people who came, listen to the presentations. I'm gonna give a couple of speakers just 1 minute to catch their breath, drink some water. But when you're ready, please come to the front. Everyone in the audience, if you have questions for the presenters, I'm gonna leave my laptop up. If you guys want to reference slides from your presentation, they'll be open. The judges, please return to the judging room and we will go over the results. We'll be back in a moment to announce the winners.
Thanks, Josie.
Hey. Come on up. Do we have any questions online? Um,
No, the amount about firefighters connected equipment.
come on up. If anybody has any questions, if anybody online has any questions, please put them in the chat. Does anybody in the room have any questions? Yes, sir.
Introduced to get rid of the dye. Are these in liquid form or powder form?
Textile dyes, you mean?
No, your
Photocatalysts are actually heterogeneous, so they are solid actually, liquid.
Okay, so they're solid and liquid. The reason I was asking is relates to the particles were very small. I think you said 10 nanometers or something, and I was concerned of an inhalation hazard if they were just a powder.
Actually, this is, we have a two things we have to consider. One of them is crystalline size and the other one is appearance size. The appearance size actually is not as least as what I mentioned. It was actually the size of crystal, which was 10 minus 10.2. And why it is important? Because in optical properties, the crystalline structure and the crystalline size is very important because they actually make a role to absorb light and to actually go for the next generation. But the size of the particle, which we can see on the actually microscope, it is not it is not very small, as I mentioned in 10.2. It is sometimes even maybe comes to micron size. Yes. So yeah. Yeah.
Thank you.
Any other questions? Yes, Jack.
On your catalyst, is that readily available or did you have to compound various atoms to make the catalyst? How did you determine those particular atoms for the
To produce it. So we have to find, before answering to your question, I need to say something. First of all, we have to consider what is the important parameters in a photocatalyst. The first one is energy band gap. What is the distance between valence band and conduction band? Because it determines what kind of wavelengths can be absorbed. If it is UV, visible, or IR. We know that actually UV is just 5% of sunlight and around 42 to 45% of the sunlight belonging to visible light. So we need it absorb visible light. So this is the first thing. The second thing actually surface area, because this is actually a redox reaction which is happening on the surface. So we have to make sure that how much is the surface area of the nanoparticle. So why I choose this actually element? First, the first thing is that I need to monitor the distance between the valence band and conduction band because it makes sure that it actually determines that what kind of wavelengths can be absorbed. So nitrogen as a element which has actually p orbital. First of all, it is the main crystalline size is dioxide titanium. Titanium actually is in the conduction band and oxygen is in valence band. So nitrogen with the p orbital can react with oxygen which has p orbital and it increase the valence band. On the other hand, cerium with having d orbital, it can react with titanium which has d orbital. So it decreases the conduction band. So by increasing valence band and decreasing the conduction band, we can reduce the energy band gap. Why is it important? Because dioxide titanium as a very important photocatalyst, it has one problem. If the energy band gap is 3.2 electron volt, so it just can absorb UV light, and we need a compound which can absorb visible light. So by reducing the energy band gap, we know that the relationship between energy band gap and wavelengths is opposite. So if we reduce the energy band gap, we can assume that it can absorb a higher wavelength from 400 to 800 nanometers. That is why actually we choose we test different type of element. But finally, this is the rationale behind our fact. Nitrogen, cerium cannot do like this. And what is the actually role of cobalt? Cobalt actually can reduce the size of the crystalline size. So because we know that if we can have a less size of crystal, we have a higher surface area, which is a very important role as a photographer. So these are actually the rationale behind them. Yeah.
Any other questions?
I should have studied more physical chemistry.
Any other questions? I have a question for all of the presenters. Can you give one at a time, can you give a brief description of what's next? What are you going to be looking into next in your research? Can you start?
Yeah, the next part is basically, as I told before, that the thermal conductivity is an intrinsic property. So it doesn't change with the number of layers, but it gets changed when we change the orientation of the fiber. So you can change the orientation of the fiber layer by layer, and you can analyze its impact over the final conductivity and the final resistance. But that's going to be the next part of the project.
So for my research, I would say my next goal is to find out all the PFAS sources, especially the fire ground. We have talked about the water compounds or particulates from the fire grounds, but we have not done anything yet. If we are burning the regular household materials like couches, carpets, where you have the PFAS treatments, what actually coming off through the smokes and this kind of stuff, so that we have a better understanding all the sources they are exposed to PFAS. So once we have the understanding, then we can prepare the firefighters to defend them.
Thank you.
The next steps for me are looking at vapor in the head form, so trying to figure out how we can measure that in our chamber. Also making sure that the silicone skin on the head form does not absorb too much vapor that it results. So lots of trial and error there. And then we have our wear trial coming up in March.
And the next step of my work actually is because we know that the photographer is surface area, and the combination of electron from conduction band to valence band is common. So how we can use a cover which can actually help it, and I'm going to use a natural polymer such as in the form of biogel, so I can actually encapsulate nanoparticle into it. By this method, I can have a higher surface area which can be obtained from processing of polymer of chitosan, for example, as a natural polymer. Also, I can avoid a combination of electron because it can make a role as a conjunction to avoid the combination of electron from conduction back to valence band. So the next step is using and finding a proper natural polymer to use for biology.
Very good. Thank you. And yes? Yes.
Are there like a set standard for, and maybe the first hour to 4 hours is there I don't know, fire equipment, is there a pre-established standard that says the ease of breathing in hour 1 to 5 is this, with particle level this? Does that exist, or do you find that you're just this being new and you're exploring, all the different headgear, that's something that could happen, or do these headgears already have some sort of standard attached that seen in comparing different options?
Yeah, of course. Currently, there is a respirator standard. NIOSH has 40 CFR Part 84. So that has your maximum inhalation and exhalation resistances, which are 350 and 250 Pascal. However, we want to keep in mind, if you looked at the N95, if anyone's worn an N95 and tried to exercise, it's not very comfortable. And that's about a moderate workload here. So if we're doing that for extended periods of time, even if it falls below 250 or 350, depending on your breathing direction, it's still not going to be comfortable to wear for extended periods. So we do have a standard. There is a way to measure it, but it's not necessarily practical for some of our wildland firefighting applications.
You see it being like, this is the mask we wear for hour 1 to 2, and then you switch to this mask, and then there's a longevity mask. Like, how do you guys see that?
I definitely think we need a multifaceted approach. It's not gonna be one respirator that fits every situation, depending on your proximity to the smoke. Like back at base camp, you really don't need as much particulate protection or as much protection. You can focus more on the particulate side. However, it is difficult because we have to get stations to buy multiple products. They have to carry it all with them in their pack. So ideally, we would have different products for different smoke exposures, you know, maybe a capper when you're in the smoke, an N95 or a face covering when you're back at base camp, but applying it in the field will be challenging.
Thank you.
And you got a question?
Yeah, a question for you as well, Melissa. Sort of similar, but I noticed in your chart with all the efficiencies that the filtration efficiency was higher for higher breathing rate for most of your products, but some of them were the inverse. Was there something about those particular ones that you could assign why that would be the inverse for those cases?
Very, very good question. Theoretically, we would accept it to be lower because it has less resonance time through the material, less time to capture those particles. So we're seeing that in a lot of our certified respirators. They're performing as we would expect, but they're also made of layers of non-woven material, depending on the filter that we're testing. Our cloth face coverings, and I saw this as well, we used to test barrier face coverings around the pandemic. They tend to behave a little bit differently. It largely varies by material, and I wish I had a better answer for you there. We're still trying to figure out why some of them increase and some of them decrease. But for that gator in particular that increased, some of it is that our headphone breathes through the mouth. So there's a tube that goes through the mouth cavity instead of nose breathing. So it's a little bit stronger, and at that higher workload, we can actually see some of these products being pulled in. So then you're looking at evaluating a surface area that's this big, as opposed to the entire product base, because it's actually pulling it into the mouth. So that might be some of why we're seeing those higher filtration efficiencies at that higher workload.
And asking that one right away, have you looked into rather than the vacuum effect, but actually the same study just being blown through the mask? Are you, or I don't know if you have looked, but if you have, do you see any correlations there between the data?
Like rather than sinusoidal breathing one
Yeah,
direction.
but airflow from the wildfires, right? Like blowing into the face covering, did that had any impact on the filtration efficiency?
Actually have tried, we've done some preliminary work in the field where we set up a bunch of stationary head farms with pumps that pull the particulates out. It's still a work in progress, but we were able to see differences in the particulate accumulation inside.
Thank you.
Thank you.
Thank you all. Any other questions? Yes, sir.
Washing. Assume when you did the washing, all three layers were actually in place. Is that correct?
Oh, no, sorry, I didn't mention it maybe during the presentation. So when we did the composite washing, we washed the outer shells in one group and both the inner layers like moisture barriers and thermal liner in a separate group, because that's how actually firefighters wash their gear, because the washing cycle is different. Because the outer shell is more aggressive, because if you do inner layers with the same wash cycles, the membrane may be, yeah, so that's why like our groups were different. Both the inner layers were stitched together, so they can be washed together.
I see. Okay. Thanks. I didn't get it. You may have said it, but I didn't get it. Okay, thanks.
Yes, ma'am.
For you as well, so can we assume that, one, we're getting a lot of PFAS washing off into our water because of, and two, have you done any research as to the effectiveness of PFAS being put on the fabric after it's being washed? Is it as effective, or do you lose the effectiveness?
So, excellent question. So it definitely yes. During the washing, you are losing a lot of PFAS, so you actually draining those PFAS. And regarding the performances after the aging, yes, performance loses a little bit, but it was not as high. I would say because most of the PFAS we detect in the new condition is residual PFAS. So your detection is very high, but most of those PFAS are not actually attached with the fabric. Those could be contaminations or residuals or unreactive or byproduct, whatever it is. But when we wash those, you're first of all, you're losing those papers. Those are not attached to the fabrics. So technically, by using that papers, you will not lose any performance. You'll only lose performance once there's the degradations on the durable water repellent finish itself. So yes, we saw some degradation, but it was not that notable. Like in new condition, if our repellency was 95%, after the aging, we detected like 1992. So it was very, very high than the current. But our aging was not very intensive because maybe it is like 1 year or 2 years of aging, what we have done. But yes, definitely if we do more aging, eventually we'll see more degradations and there will be performance loss.
Anybody else? Those are some great questions. Diane, I'm sure you're wondering about something. No, not today. Okay, Jack, anything else? Well, thank you very much for everyone.
Judges have spoken. I think we want to first of all thank all the 4 presenters for their excellent presentation. And equally important, thank you all for really staying here, participating and encouraging these students. So I think that really has a lot of value. So thank you. Okay. Here are the results. The 4th place goes to Yaya Absalon from Georgia Tech. University of Georgia. Come on up here. Come on up. Please.
Set those you over there. I'll hold on to this. This is for you, sir.
Thank you.
Congratulations.
Thank you.
Congratulations.
We have to look over there.
You guys want to step up a little bit?
Oh, yeah.
In the
Oh, okay.
presentation.
All right. There we go. Thank you. Thank you. Good.
Perfect. Thank you.
All right.
Congratulations.
Thank you. And the 3rd place goes to Hassan Ali from
Hassan have come all the way from Pakistan.
Oh, man, yes. Congratulations.
Congratulations. Thank you for coming so far.
And the 2nd place winner is Melissa Armstead. Thank you. And first place we have is Noor Muzumdar. Thank you. Thank you, everybody.